Everyone, this is Dr. Walker. This is video 267 called self-inductance. Let's talk about the concept. The first thing is that we're going to have an inductor, which is just a coil of wire. And there's going to be a changing current within this coil of wire. So imagine that you just have a coil of wire and there's no current going through it. And now let's say that you hook it up to a battery, so that there's a positive voltage on the left and a negative voltage on the right. Once you hook it up to this battery, you now have a current through this coil. So the current through the coil is changing. Now, we've learned that a solenoid will produce a magnetic field when there's a current going through it. So there is now a changing magnetic field through this coil because of the current. And now let's think about Faraday's law. Do you remember Faraday's law? It said if the magnetic flux through a loop is changing, then an EMF will be induced. So once there's a changing current through the loop, there's a changing magnetic field, which leads to a changing flux, which leads to an induced EMF. So that's the concept. So that is what the second bullet says, that there's a potential difference or induced EMF when the current through the inductor is changing. And the direction of the induced EMF is going to oppose the change in the current. And we learned about Lenz's law that told us about the direction of the induced EMF. So in this case, if the current was increasing clockwise, then the induced EMF is going to produce a current counterclockwise to oppose that change in that increasing flux. So the EMF induced along the inductor would have a positive on the left and a negative on the right, so that it would oppose that increasing current. So that's all the concept. Let's look at the equation for self-inductance. So you can think of it as the self-inductance of your inductor is going to determine how much or how well it opposes that changing current. So the self-induced EMF is proportional to the rate of change of the current. So the EMF is proportional to how quickly the current is changing. But the self-inductance, we use a letter L for it, is going to tell you, well, how well is it going to oppose that changing current? If you have a large inductance, then you know that you're going to have a large EMF induced. So that means that an inductor with a large inductance is going to oppose a changing current very well. So we're defining inductance within another equation just to understand it conceptually, that the inductance of your inductor is going to affect how much EMF is induced by that inductor. We do have another equation for inductance. If we're talking about the solenoid, then the actual inductance is going to depend on the properties of the solenoid. Just like when we had resistance, the resistance of a resistor depended on the properties of that resistance, the length, the area, the resistivity. Well, here, if you have an inductor, the actual properties of the inductor, such as N, which is the number of turns, or A, which is the area, right? When you have that inductor, the area of these loops here, and then L is the length of that inductor. So all of these factors will affect the inductance. The more turns, the bigger the area, the more inductance for that inductor. So it would just be a plug and chug if you had to find the inductance of an inductor given the number of loops, the area, and the length. And mu naught is the permeability of free space. The unit for inductance is the Henry. So that's just another unit, and it has a letter H. Let's take a look at an example. What is the self-induced EMF in a coil of 5 henries, so that's the inductance, if the current through it is changing at a rate of 150 amps per second? So L is the inductance, and then the change in current per time is given as 150 amps per second. So we just saw two equations that had inductance in it, but we have to pick the one that's going to be more useful, and that's going to be the first one that we saw. Now, we don't really care too much about the negative. That's just to remind us that it's going to oppose the change in current. The EMF induced is going to oppose that change in current, but if we just want to find out how much EMF is induced by the inductor, we really don't need that negative sign. So we can just write EMF equals L times delta I over delta T. L times delta I over delta T. And then just plug and chug. L is 5, and the change in current per time is 150. So that's going to leave us with 750 volts as the EMF induced in this inductor. So again, you can see that the faster the current is changing, the more EMF would be induced. Let's look at one more question. This is your turn. It's asking, for which inductor is the current changing more rapidly? What the picture is showing us is the inductance of each inductor and the EMF induced. So try it on your own, and let's take a look. Using the same equation from the previous problem, EMF equals L times delta I over delta T, and we're looking for the change in I per T. So delta I per delta T is going to be EMF over L. So all we have to do for this one is do the 2 over 2 for this one and the 4 over 1 for the inductor on the right, and we can see that the inductor on the right, the current is changing more rapidly. It would be changing at 4 amps per second versus 1 amp per second. So that's it for the concepts of inductors and self-inductance, and in the next video we will be placing them in our AC circuits.